give you the proper introduction. Okay.
All right.
All right, Tom. Tom is a natural resource specialist with UC Berkeley, who, by the way, is housed where he was brought up near UC Riverside. So Tom is a former member of the Integrated Hardwood Range Program, which unfortunately was disbanded a couple of years back. But that hasn't stopped him from having a very active interest in oaks and their persistence in the developed landscape. So we're very fortunate to have Tom. Now, I've been working with Tom on his presentation over the last week or so, and I got to say a few things at the outset about the oaks, okay? First off, the guide that's been provided to you by CAL FIRE to do the greenhouse gas reduction analyses doesn't address oaks at all. It's totally conifer-centric. And so, when we discovered this to our horror, we scrambled around, and Tom graciously agreed to do this presentation. We got to tell you that the models that exist for conifers that we talked about last week don't exist for oaks. The forest vegetation simulator, coal, the carbon online estimator, none of that stuff works with oaks. Okay? There's very limited data available for how oaks grow or how they respond to treatment. Some of the work that Tom will talk about today was done by Rick Standiford and his colleagues at Berkeley, by Mike De La Soe, and by Pillsbury down at San Luis Obispo. So there isn't a heck of a lot of information out there. We spent a little bit of time trying to gather it together, but this is working with the oaks in this context of greenhouse gas estimation, is very new. The ARB biomass equations that are posted on the website do exist for oaks, but if you're going to use them, then you have to measure the oaks. So with that preamble, I'm going to turn it over to you, Tom, and I hope that I haven't stolen your thunder at all. But
no, not at all. Not at all.
Okay, there you go.
So what I want to try to do today is give you a sense of what oaks are and why they're different from conifers, and then to talk a little bit about how people might go about looking at sequestration of carbon given those constraints. So to start at the beginning, it's always good to go over the species that we're working with, because I think people have a sense of oaks being oaks, and because they haven't been a commercial property, and because we haven't used them for a lot of purposes other than aesthetics, or that we don't really have often a good sense of how many oaks we have and how they separate. So the first thing is there's three groups of oaks. There's red oaks, white oaks, and intermediate oaks. These are the subgenera within Quercus. And they've been around for such a long time that the difference between red oaks and white oaks is like a horse and a cow. You really have some big differences between these species. But for the time being, just sort of recognize that when someone says, I have an oak tree on my property, it doesn't mean that you can apply any equation without knowing what that species is and maybe its growth form. I'll talk about that in just a moment. I do know that currently the FVS uses a lot of the oaks as interchangeable units, and I want to sort of express in my presentation a little bit why that can get you in trouble. So this is a slide which basically shows you growth forms of oaks. We have a range of growth forms, and it's sort of surprising that the families themselves or the subgenera themselves don't necessarily sort out on these, but we have single-stemmed oaks, multiple-stemmed oaks, kind of intermediate arborescent oaks, and then what we call our shrub oaks. And the stem oaks, the single-stem oaks, really are our trees. Multiple-stemmed trees have a look of being a tree, but if you look carefully at a canyon oak or an interior live oak, what you have is often multiple stems, and in many ways they're acting like a shrub that has become arborescent. And that's really important when you start to talk about how trees sequester carbon how they survive things like fire and other things. Differences can be notable, and one of the things I wanted to point out, just to reinforce this point, is in this picture, you can see coast live oak here and an interior live oak. First of all, kind of look at the size differences. These are sort of typical. And in many cases, you have a very large bole in the coast live oak, and you have multiple stems, which you can't see because the canopy is so thick. But if you look up above at the picture, this is, this gives you a sense of how thick the bark is on Quercus agrifolia and how thin the bark is on Quercus wislesinii. Again, that doesn't necessarily enter in as much into the carbon calculations because bark is often very close proximate to wood in terms of its characteristics in many of the equations. But the important thing is that for the same diameter of tree, you can have 35% bark on the Quercus agrifolia and never more than 10% bark on the Quercus wislesinii. But superficially, when you'd walk up to this tree, they would appear the same. Another example of this is Quercus chrysolipus, again, a multiple stem tree. We often come up on these trees and imagine them to be very, very old with diameters that can be 10 or 12 feet. But there are a bunch of stems that have grown together, and that's a very different growth model than if you actually had concentric rings coming out of a central core to the bark. So just some things to think about, that growth form is really important for maybe management, perhaps more than some of these carbon calculations, but when you start talking about them being interchangeable, if you have a single bole and a multiple bole, this can have a dramatic effect on how you basically calculate your carbon. So the second thing that I think, you don't get anything else from my talk today, but just this understanding that oaks are in what I would call a transition between the very dry vegetation types in California and the conifers or the reliable precipitation areas of California. And I know that I actually saw that John Helms is on here, and I don't want to sort of make this oversimplified. These are very kind of complex ideas. But just for the point of illustration, I want to sort of emphasize that when you live in a transition zone, you do different things. And one of the things that oaks do remarkably well is they respond to precipitation, so that gives them persistence. And it's a very different model than if you're thinking about growth rates that would occur in someplace like a conifer whose choice is to grow or die. And I'm going to bring back that point many, many times. But so this area that we talk about as a transition zone is actually millions of acres in California. And not only does it comprise an area where we have a lot of oak woodlands, but we also have a lot of challenges that take place with development. So projects that come in and work on sequestering carbon may actually in some cases find more success in this unpredictable environment challenged by development than they might find at higher elevations, especially when we talk about restoration. So just to illustrate the concept of transitions, these are all curves of evapotranspiration and precipitation in parts of the hardwood rangeland or the oak woodlands. And the intriguing thing is you have curves where basically the evaporation potential measured in inches, just like precipitation, has a high point in the middle of summer, as you might expect, and then declines with the fall and going into the winter. But what's really kind of odd is that for almost every place on the world, you have a potential to evaporate more water out of the system from basically heating and solar radiation than you have rainfall that comes into the same sort of system. Since we have Mediterranean rainfall, we have our heavy times of rain that happen from the fall and then into really the months of February and March, and by May, pretty much all of our systems are not going to see rainfall until the next October. What that means, though, is when you're behind the redwood curtain at the start of the conifer systems, you really have about 6 months out of the year when you are above average. You're in sort of a positive situation, as opposed to being in the deficit where you could pull more water out of the system than is coming in. When you get up to San Luis Obispo, which is really, I'd sort of say, the heart of oak woodlands, you have about 4 months out of the year when you have basically this positive situation where your system is basically wetter in a sense than it will be in the middle of summer. When you get down to Descanso, and I put Descanso here, this is in southern San Diego County, but it's kind of a surrogate also for the southern San Joaquin and in fact many areas in the Sacramento River or the Sacramento Valley. What you get is basically you get about 2 months out of the year, February and March, when you're a little bit ahead. You're in basically deficit for the entire summer and fall, and maybe you pick up a month in December and sometimes in November when you're neutral. So this period right here is a tremendous amount of stress which occurs to oaks. In Riverside, which is sort of the tail end of oak woodland distributions, you never have a time when the ability to draw water out of the system isn't greater on a monthly basis than the water coming into the system in precipitation. So this is the system, this transitional system that oaks have to survive in. And they've done remarkably well for a number of reasons. Oh no! Well, this is a transition. This picture right here, I guess I can do the equivalent of a hand animal, shadow animal. This should be a graph that shows you a whole lot of cord Engelmann oak trees and the fact that we have spikes which basically coincide with periods of wet rainfall. Now this would have shown you a standing biomass of by ages of trees. And there's some problems with that, but just you have to take my word for it. I'm a little embarrassed that there's nothing there. But when we have bouts of rainfall, like we go through a wet cycle of 3 or 4 years, that's the time when an awful lot of oaks recruit. And when you have these bouts of drought, like we're currently in for 5 years straight, you just don't see the same number of trees coming into the population. So oaks have the ability, because of masting, to take advantage of these wet opportunities and to really sort of restock an area which might not have had trees. I'll get the guy off there. That's terrible. So this is 1990 to 2003, which is actually one of the wetter periods we've had in Southern California, to show you that all of those blue circles on the right-hand side of the picture represent oaks that were recruited from 1990 to 2003. And you can sort of see the canopy area that's producing these trees. But that's a remarkable number. It's 45 trees that have been recruited, and some trees that are the red circles which have been lost. But oaks have this capacity to recolonize an area after a disturbance. Now, this is not a new area that didn't have oak trees before. These gaps were not places where there were never oaks. This is actually a case of tremendous overuse before a property went into ranchettes. So this represents the capacity of oaks to take advantage of good rainfall and survive in this transitional system by being able to have a reproductive traits that give them a lot of capacity. Richard, this is going to be a real nightmare for me if this goes all the way through. I'm not exactly sure what I should do. Richard, you there?
I'm here. This is unfortunate, and maybe because we didn't have a chance to test this out on the website beforehand. I don't know how many are going to be like this. What we could do, and poor Mike's internet is down. So let me quickly go through the whole thing here and see what's happening.
Okay, well, I can just keep sort of talking so people don't have to sort of just watch a
Yeah,
screen.
I think you'll just have to do that, and you'll have to, we'll have to bear with the problems with the graphics. I don't think we can backtrack.
Just to kind of come back and maybe give you a broader view so that the slides won't guide you anymore. But what I'm trying to explain is that when you have oak woodlands, that these trees are able to stay in a place, and persistence becomes extremely important, but you have to have a lot of workarounds. If all you're worried about is growth, and you're competing in a system where there's sufficient amount of precipitation that you never really have to worry about, it's not as much a part of the equation, you have a different set of life history traits. Oaks do a tremendous number of things, and in this case, this is a picture that would show you that if you get to a safe site as an acorn and grow, you can grow remarkably rapidly. You can get a yard of growth a year, a meter of growth a year coming out of a seedling. But if you're not in the right place, you're still not necessarily going to be a mortality. You're actually going to be something that sort of holds on for maybe 6 or 7 years before you actually take off and start to grow. Again, all these strategies that oaks employ to stay in places where the rainfall is not as predictable. Yeah, hopefully these things will disappear at some point, but this goes back to this idea of masting. In some of the species, particularly the white oaks, they're able to mast after 4 or 5 years. This doesn't seem to be the pattern in red oaks, but again, if you can imagine that something's going to live in a landscape for 150 years, it can produce 5,000 acorns in a year, and it can start to do that after 3 years. That gives you an idea that that's one of the ways that you can respond. The same way that you can respond is resprouting. So between all those characteristics, what we see is that oak trees don't have a logarithmic rate of growth, and then succession is death if you don't have the right resources, if you have a drought. And what oaks will do is they will get larger over time. They'll persist in a landscape for a very long time, and then slowly they'll begin to lose their biomass. And since the 16th century, people have said that oaks live for 100 years and die for 100 years. Now, those two curves I've presented in front of you, I think are really important in the sense that if we're not worried about being in a transitional environment and we have resources that are not necessarily guaranteed but maybe predictable in the landscape, you can get logarithmic growth, and that produces a certain kind of tree in the forest that we have at higher elevations in California. With oaks, we're going to see that the amount of biomass that a tree locks up changes over time, and it's this part of the graph that becomes important. So, maybe we could sort of say that this is the same as we're seeing in conifers, that you have some sort of curve. I've made it sigmoidal. I mean, certainly there's times when it's logarithmic, but you reach a point where the tree has tapped out all of its resources that are available, and at that point the tree can no longer outgrow problems like beetle damage or pathogens, and it begins to slowly decline. And this is a general model of angiosperms anyway, but angiosperm trees. But the important thing is that this part of the graph has to be taken into account whenever you do your carbon calculations, because you can't have this sort of idea of kind of like a growth that's going to happen and be guaranteed and continue sort of in a non-ending manner. On top of that, because they stay in these places where the climates are transitional, oaks have a remarkable amount of plasticity. And within one species, you can see a huge number of strategies for basically you get as big as you possibly can. You try to grow later if you don't get a good root system initially. And that kind of plasticity is great for them persisting. But when we come to try to predict how much carbon we're going to have on a landscape, you can see that this becomes a much more complex situation. These would have been two curves. I'm just going to give you the R values. If you guys ever taken statistics or you've heard people talk about correlations, when we try to correlate diameter with age, we end up with an R value that's basically worse than random. It's about, the R values are 0.13. So diameter is a very poor predictor of age when you cross-section trees and you count the number of rings that are actually inside them. This is out of a sample of about 2,000 trees that are Engelmann oaks, California black oaks, and coast live oaks. And so I know you can't see the graphs, but when we try to look at annual ring growth and diameter, we get a much better correlation. And so the point is that if you get to the place where you can grow as an oak, you grow, and if you don't get there, you don't grow. And so you can have very small trees that are actually quite old and very large trees In fact, the largest trees we find in oak woodlands typically have very large growth rings and are not as old as some smaller trees. So the big monsters that everyone always says are 400 years old, which I'm not trying to disimbue people of kind of the romance of trees that might have been around when the Spanish first arrived, but those trees are often only 150 years old. And in fact, it's very hard to find a lot of at least the red oaks that survive past 300 years. So the point is that you cannot use swapping this around. You can't use age to predict how big an oak tree is going to be unless you already have kind of an understanding of that particular oak tree and what it's done in the past. So getting back to this concept of conifers maximize growth, oaks maximize persistence. When you try to come up with models to predict stand biomass, conifers are really good for this, and I think people have actually figured out most of the woes associated with variance in these models, and they really have turned out to be probably one of the better success stories in ecology. When we try to do the same thing with oaks, what you find is with all of this plasticity and all the quirkiness that occurs as a result of these trees sort of responding to their environment in a much more flexible manner, the curve you get is not logarithmic. And in fact, a mathematician will tell you that when you sum a whole bunch of wavelets, it's very hard to get any kind of a simple curve. What you end up with is maybe at best a polynomial, but the reality is this thing, as my son, the mathematician, scolded me about, this is not even necessarily a polynomial because it's really hard to model this. It's not impossible, but what you have to do is you have to do it empirically. It's much more difficult to start from a global approach of, say, statewide, we're going to look at biomass accumulation, and then work our way down to the variance of a given stand. It's much more difficult to do that with oaks. And I'm not saying that when you have this stand biomass curve that it doesn't have a little wobble to it, but this is a logarithmic curve with a wobble. This is a wobble that might have places that are occasionally straight. So you have to take a lot sort of more of a local approach to looking at this, or you have to go out and empirically collect a large amount of data and then build the model up from the tree and stand level. And that's really important when we start to talk about using things like coal and FVS for our estimation of carbon in oak woodlands. So given that there's a lot of idiosyncrasies, these are all the models that I found that the Forest Service put into a publication, and I think it's sort of a good survey of things that people might suggest that we could use. And again, if we stick to the level, where's my arrow? If we stick to this level of local as opposed to trying to scale up and start at a global perspective and come down to calculating our carbon sequestration in oak woodlands, if we stick to this local level, then in reality we expand it to maybe this thing. We end up with about 4 models that we can really end up maybe perhaps using, and it's going to get a little more dismal even as I work through this, because I think there are reasons that I just showed you that sort of defy why some of these models have a difficult time working. So these are the 4 models that have the greatest potential for helping out in people's attempt to do models. They're COAL, which is the Carbon Online Estimator, the CTCC model, which is the Center for Urban Forestry, there's FVS, and then there's iTrees. And these are the 4, and I've got the websites up there, so this will be something that you can look at later. If you look at these, let's start with whether or not you have to collect data. And in the case of iTrees, you don't even have to collect data. FVS, you have to get the stand data out of the system, the FIA data out of the system, and then manipulate that. COAL, you don't have to collect anything. You just take the straight FIA data. And I'm sorry, when I was talking about FVS, what I should have said is that they actually suggest that you go back and do measurements, or that you correct for what they have given you as tools. In all this, iTrees only uses DBH, so there's no way to calculate the canopy, and you start sort of falling off in terms of being estimating the ability to estimate the actual amount of canopy and things other than the bowl. CTCC also uses only diameter and unfortunately has a limited number of species because it's an urban tree model, and so they're using basically the horticultural trees that we have in California rather than native species. FVS we found a lot of problems with. One of the biggest ones is they use variants to get you to get a better handle on this, but you're starting from a global model and then putting variants in. Unfortunately, it treats all those species, including the two species I showed you with those remarkable differences in bark thickness, all are treated as a single variant or a single kind of super species to use in these models, which makes them difficult to have a lot of confidence in. So none of these models, as Richard said, really sort of do what we want them to do in terms of generating a lot of estimates of carbon. That leaves us sort of saying, well, geez, do you have to count every grain of sand to tell you're on a beach? And this is something that we don't want to have people have to do. And in science, I mean, we don't like to think that that's the way that necessarily our data should be collected. So the biggest thing we think that you have to do is you have to have some kind of stand-based or individually based model that you work up from. I think that you can group data by stage, that is a growth stage, and so you don't have to measure every tree in the forest, but you should have reasonable categories like acorn seedling, sapling, canopy tree, declining tree, irreparably declining tree, and then within that group you can probably come up with descriptions which may allow you not to have to measure every tree that you're working with, which seems like too much work, and especially since we don't have a lot of time before these grants actually have to go in with some kinds of estimates. So getting back to this notion of this is our individual tree, and over time our individual tree is basically going to do this growth to a point where it asymptotes, and then it's going to decline in some manner out to the other end. If we take this as an idealized curve that would be maybe in the absence of a lot of problems like fire or insects here, so you have a nice long period of time when it's sequestering carbon and it's stable, it's not getting bigger, but at the same time it's holding that carbon for, say, a period of 100 years. That's kind of our idealized curve. And one of the things we can do is we can then go back and look at the business as usual models. Just to refresh your memory, that's the term people use for what is happening in a landscape in terms of carbon sequestration, which will be your metric for measuring how much carbon you're actually going to take out of the atmosphere and turn into some kind of wood product. So the business as usual model for an area that has no trees is the easiest to describe, because now we're talking about a line where you're not adding any biomass and you have no carbon sequestered initially, other than the grassland and whatever might be there, including in some cases bare ground if you have a place that's highly disturbed. So then this green area becomes the amount of carbon that you're going to sequester in a tree over time. And this is one of the easiest models and probably one of the easiest ways to imagine it, and it's one where you may not have precise models, and the models that we have are going to be ballpark and not necessarily completely accurate, but at least with the data that's been collected by Rick Staniford and Norm Pillsbury and Mike Delasso and some others, we think that we may be able to give you numbers that you could at least sort of massage to say that this is our expectation for what we will get if we plant a number of trees and then watch the carbon accrue over time. So you can actually use models like the CTCC model for coast live oak in the Inland Empire and in the, I think in the coastal areas, but you can't use it to measure coastal areas in the Southern California region. So you can't measure coast live oak in the coastal regions of that. So there's obviously some drawbacks, but these models are something that will at least get you started in trying to figure out if you're in the right ballpark for estimating it. And then more important, I think that you're going to have to go look in the literature and look at oak growth rates that have been calculated by people from empirical data. Then look at the models that take oak biomass and turn that into carbon. And there are some in a number of different books that give you sort of ballpark figures for how much carbon comes out of bark and wood and these sort of things. And then you do have to go back and probably figure out where you are, and there are some things you can use in the way of climate so that you don't sort of try to imagine that you can use something that, data that was taken out of a really wet system in San Luis Obispo County and then apply that to oak trees that are on the margin of the desert in San Diego County. So anyway, we're not giving you a lot in that regard, but I think that this is at least an area where you can get some information. Am I still on, Richard? Oh,
You're still on.
good. Okay. My phone went dead for a second, and forgive me. That's sorry to sound so provincial. So now switching over, we have other things that we have to try to estimate with carbon sequestration and how much carbon can you bring into a system where it's got some other business as usual model. And one of the ones we have right now in California is a case of oak decline and mortality associated with pathogens and insects. This is a case where, if we can imagine our idealized oak tree biomass over time, that you have an incident where an insect attacks a tree or a pathogen attacks a tree and it rapidly declines and becomes dead. So in this sense, the red line represents our base business as usual, and what we're going to do is calculate the difference between that area and this area in the green. The problem is that when you get to this point in the tree's sequestering of carbon, that is, it's about asymptoted in terms of how much carbon it is actually locked up from the environment. It can be really difficult to figure out how long that carbon is going to persist as dead trees in the environment. So which one of these lines do we use to calculate the area above for the amount of carbon we're going to hold for a period of time that if we make some kind of activity, which basically means that this tree doesn't die. We don't really have a sense of what our business as usual model is because we don't really know dead carbon in the environment for oaks. And there are other things that happen as well. People tend to remove trees if they're close to structures. There's fuel breaks. There's fire hazard reduction. So there are a lot of things which are kind of unknowns about this. I do want to kind of give you an example of maybe I don't want to give you an example. One of the things we worry about with all of these problems that we have with sudden oak death, with gold-spotted oak borer, with polyphagous borer, with almost every problem is that it's not just that this problem is spreading through the environment. It hits places where it seems much easier to pass from tree to tree, and it's much easier to have individual trees within a woodland amplify the problem. In the case of gold-spotted oak borer, you have places where the beetle is present but is not killing large numbers of trees, and then you have other woodlands where for some reason individual trees start to amplify the problem so that there are 100-fold more beetles coming out of these trees. If you get a large collection of those trees, now you're suddenly amplifying this by an order of, several orders of magnitude, and at that point you start seeing 75% mortality or 80% mortality. Given those conditions, there's an opportunity to come in and have some kind of management of the pest and then to not see that the mortality goes to 95% or 85%. Maybe the mortality stays closer to 50% or below. That would have been what I would have shown you in this slide. But the point is that thinking about these problems as epidemiological problems and not traditional forestry problems often gives you a handle on how much carbon you might be able to sequester should you be able to intercede and not have these things go to the point of amplification. So this just gives you a sense of one of the problems we have with gold-spotted oak borer. It's currently on about 26,000 hectares of oak woodland. It's easily killed 100,000 mature oaks, and it's wiping out the coast live oak and black oak forests of San Diego County. It's like the biggest change occurring probably in these woodlands since the Pleistocene. So just to give you an example of when you have these cases of amplification, that here's our stand before it was attacked in 2002, and here's what remains of the stand in 2009. I should have updated this. It's gotten worse. The trees that are left are all very small diameter trees, and many of them are hybrids with Quercus wislosinii, which isn't attacked by this beetle. So we basically wiped out all the coast live oak, which are susceptible to this beetle because it's been introduced from Arizona. Same kind of situation is happening certainly with tan oak and areas in Northern California with sudden oak death. So the last model I wanted to talk about is the business as usual for biomass reduction to fire, and this is probably an area where we have a tremendous amount of questions, but I just wanted to show you to conceptualize it. If you think about, again, our individual tree and what an individual tree will do, at the moment of a fire, basically you can literally drop the biomass to zero. I mean, even the roots can burn in some cases, but if the roots don't burn, you may actually see recruitment again, and you'll see resprouting, and then the tree at some point will rejoin where it would have been. So now our model becomes this area right here, which has been affected by fire. Now, if this is a natural process, somebody might say that your business as usual model cannot say that this is something which we could call as a carbon benefit by having some kind of different management. But at the same time, I think that there are certainly cases where people have proposed thinning or these sorts of things. And if you try to imagine that you have this dip in the biomass that's going to slowly accumulate back again, that's the place where some kind of management action with fire would be calculated. And I don't know. I think I'll leave it at that because I think it's a little more controversial than a lot of stuff. That wraps up what I was going to talk about. I think that when just to reinforce this concept of global models, which we then pull down by variance, and I'm not trying to pick on FES, but I think there are times when these things are really good for what they were made for, and when we try to adapt them to other systems, the number of constraints get you to the point where the model isn't really functional anymore. And I wanted to reinforce that by just talking about the fact that, our the common red oak species that we have in California have probably been somewhat isolated and evolving on their own from the red oaks in the east for probably 20 million years, and the high density of species in the Mexican red oaks for probably 5 to 10 million years. And so we really do have kind of a unique situation with our hardwoods in California with a Mediterranean rainfall system being divorced from the eastern red oaks for an exceptionally long time. And to make that point, I think even further about and I actually talked to Kenneth Starr about this, and he told me that I could be a higher provincial because higher provincialism is something that Californians have exercised for a long time. But the truth is there really is no place on earth like California. This is San Jacinto Mountain, which has a whole lot of oak woodlands and conifer forests on it. And the east side of San Jacinto Mountain is the greatest scarp in North America. On the top of the mountain, we have red-breasted nuthatch, and this is a species that goes north into boreal Canada as far as there are trees, and it finds its southern terminus on top of this mountain. At the base of the mountain are vermilion flycatchers. Now, vermilion flycatcher is a bird that goes all the way to the equator and finds its northern terminus right here at the base of these mountains in Riverside County. So what we have is over an 8-mile stretch, you have a bird from boreal Canada basically in almost earshot of a bird which is from the tropics. If you did the same thing in eastern North America, you'd have to go about 1,200 or 1,600 miles from Duluth to Corpus Christi. The point being that over very short distances in California, we manage a remarkable amount of diversity. And in some cases, it's not the tropical forest diversity where we have 400 species of trees in a hectare. What we have is one canyon can have a completely different array of species under a completely different array of conditions because we have this remarkable topography and sort of the terminus of Mediterranean rainfall and the sort of the northern terminus of the monsoons. Now, I'm talking about Southern California, and again, maybe I'm a provincial in a provincial, but I do believe that you can find these kind of examples throughout California where there's really a tremendously remarkable change over a very short distance. And that means that it behooves us to be very, very careful when we start to talk about carbon sequestration and not to sort of gloss over the differences, which I think are very unique and interesting. And that's my talk.
Thanks, Tom. I want to sort of add on a little, what would you call it, a little tail end to this. One thing that I think you'll probably come away from this shaking your head saying, well, now how am I going to do this if I have an oak project? And that is an open question. I think you're going to have to be creative, and I think you're going to have to avail yourself of the information that's available now on how oaks grow, how they respond to thinning. You know, the work of Standiford, the work of Pillsbury, the work of Mike De La Salle, and you're going to have to sort of invent your method. And as I said, the ARB protocol contains biomass equations for oaks. And if you are going to have an oak project and you can measure your oaks, you can use those biomass equations to estimate the amount of biomass and the amount of carbon and the amount of CO2 equivalents that you have now. And you can also then try to use the growth data that are available to project your stands into the future. You can use the results of thinning studies to try to estimate how a fuels treatment or a pest management project is going to affect your carbon stocks. But it really is not very simple as compared to the conifers. So, you know, I wish you all well on that.
Yeah. Well, can I come back on for just a second?
Oh, yeah, and also, but we can take questions, too.
Yeah, I just, to respond to what you said, I mean, I think it would be a terrible situation if the most investigated systems with the easiest places to make models were the places where we put our resources to carbon sequestration. I think that the hardwood rangeland is the place where we may actually see some tremendous opportunities for it. And I want to encourage everybody, and we will do our best, you know, those of us who work in the system, to try to get this in a palatable form, to try to get things like general growth equations, and so that you can at least come forward with some sort of estimate of what you're planning on doing. I would really not want people to be discouraged from doing a really good thing because they can't come up with a precise model. And I'm going to imagine that the people who are going to be reviewing these grants are also going to have somewhat of a perspective like that as well. So please don't be discouraged. I mean, my talk was more to say don't make silly mistakes, but I think we can come up with some way that's reasonable. And also, you know, it would be a shame if we didn't have the opportunity to have people do this work and refine their models over time, because, you know, saying that we don't have the data and saying we're not going to undertake the exercise that will help us gather the data would be a real loss, I think.
Well said. Do you have any questions here? We have about 5 minutes for questions, and we might have some time at the end for additional questions. Incidentally, there was missing graphics in Tom's presentation. Really, you can blame me for that because I didn't get a chance to try it out on the site to make sure that it worked. But we will convert it to a PDF, and it will be posted on the webinar page, so you'll be able to see those graphics if you go to the site and download the PDF.
Well, it
So
was good.
I have to apologize for that.
No, it was great, because then I could just talk as if the data were compelling.
Any questions? We have a couple of questions here. Time for questions. If you have questions that come to you later and you want to forward them on to me, I forward them on